Consider this. Suppose there's a point object, okay, a very tiny object in front of a person's eye. Now, at the beginning of the chapter itself, we had discussed how we get an idea of the distance of an object from our eye based on the light entering into the eye. So you can imagine many different rays coming from the object or entering from the object into the person's eye. Okay, this is one of those rays. And the last one can be visualized like this. In between these, there will be infinite other rays from the object entering into the person's eye. Now, based on this angle, the angle between these last rays, okay, the first and the last rays, we get an idea of the distance of the object from our eye. Okay, because based on that angle, our eye will have to adjust itself. It will have to adjust its focal length and make these rays, bend these rays such that they meet on the retina and form an image. Okay, so what focal length the eye adjusts itself to depends on this angle of divergence. And based on the focal length to which the eye adjusts, our brain can interpret the information about distance of the object. We have evolved that way, as I said. Okay. Now consider the same observer and the object. We know where the object is. Okay, if you look at it directly, we can get an idea of its distance also. Get an idea of the rough distance at which the object is present. But suppose we do something like this. Just a moment, let me remove these rays. Suppose we insert a glass slab in between. Glass is also a medium which allows light to pass through it, obviously. So let's say we introduce a glass slab of significant width between the object and the eye. Now the object will still be seen by the person because glass is a medium which allows light to pass through it. Light from the object will pass through glass and enter into the person's eye. But if any of you can tell, you tell, will the object appear to be at the actual distance at which it is from the eye, or will it appear closer or farther? When you see the object through a glass slab, okay, will it appear to be at its actual distance, or will it appear to be closer or farther?
Sir, is it closer?
Closer. Okay, we'll see. Rishi, what do you say?
Sir, I'm assuming closer, but I'm not sure.
Rishi, just visualize this. Suppose you are reading something on a sheet of paper. You put a transparent scale on it, transparent plastic scale on the letters. Do the letters appear to be closer to you or farther from you? Or do they appear to
Closer.
be closer? No. So this is somewhat similar. The object appears closer. Okay. Let's discuss why, or let's understand why that happens. See, whether something appears closer or farther, or how far something appears to us, depends on how the light enters into our eye. Now you imagine light rays from this object striking this glass slab. One of the light rays from the object will strike the glass slab along the normal. When ray is incident along the normal, even if it is going from one medium to another, it does not bend. So it propagates straight through the glass slab. And again, from glass to air also, it enters in the same direction and reaches the person's eye. So this is one of the rays going from the object to the eye of the person. Fine. But with one ray, our eye or our brain cannot interpret how far the object is from our eye. Okay, we need an angle of divergence. So we need two rays at least. So let's consider another ray traveling like this. Okay, let me show the original direction of propagation of the ray. Original direction of propagation was like this. Okay, now first, the second ray that we are considering enters from air into glass. When a ray enters from air into glass, that is a rarer medium to a denser medium, Rishi, tell me, how should it bend? When ray enters from a rarer medium to a denser medium, how should it bend? Rarer means fast moving medium. Denser is a slow moving medium. How should it bend?
Sir, away.
No, it bends towards the normal. Okay, it bends towards the normal. So look at the ray that I am drawing on the right lower side. Consider a ray like this, incident at a significant angle of incidence. We know its original direction of propagation. Now it bends, if it bends towards the normal, okay, going from rarer medium to denser medium, air to glass, it bends towards the normal only. So it bends like this. And again here, okay, at the second surface of the glass slab, the light is entering from glass into air, from denser medium to a rarer medium. When it goes from a denser medium into a rarer medium, it bends away from the normal. So bending away from the normal, it becomes like this. We'll solve a problem also based on this, exactly how much it bends and all. It becomes like this. So to the observer who is on the left side of the glass slab, this ray will appear to be coming from or coming at an angle like this, not from the original position of the object. Okay. So in the upper diagram also, the ray after bending, okay, within the glass slab, and again as it emerges out of the glass slab, will appear to be coming from or will appear to enter into the person's eye from somewhere here at an angle like this. Okay. You can imagine some other rays also. They will enter the person's eye as if they are coming from that position, O dash, because of the bending that happens at the air glass interface. So effectively what happens, the object appears to be closer than it actually is. And this is true in real life also. There will be a significant deviation. As I said, you can visualize letters coming closer to you or letters appearing raised up when you put a plastic scale on a sheet of printed matter, printed or written matter. Now let us do some calculations based on this. We need to find out where exactly the image appears to be, means how close the object actually gets. There are some concepts also that we'll learn in this problem. So we know where the object is. We need to find out where the image forms. Fine. Okay. The observer is not needed. Whether the observer is there or not, image forms where it forms. What we need to know is the refractive index of the medium in which the object is present. That is air. So its refractive index is 1. We need to know refractive index of glass. Let it be mu, unknown. We need to know the thickness of the glass slab. Let it be T, that's the thickness. And we need to know where actually the object is present. Let the object actually be present at a distance D on that side. Okay, D, or you can call it L. Fine. Imagine light being reflected by that object or emitted by that object. Rays will travel in all directions. Some rays will pass through this glass slab. Now, when light passes through the glass slab and then comes out on the other side, it undergoes two refractions. One at this surface, let's call the first surface S1 and the second surface as S2. Both are flat surfaces. Okay. We can take one ray like this, which undergoes normal incidence and passes without any deviation. consider another ray like this. Okay, at a significant angle of incidence I will take. Just for us to be able to visualize, okay? Because the spherical surface refraction formula, which we derived in the last class, it's valid only for paraxial rays. Now this big an angle cannot be considered paraxial, but for us, for our visualization, we take it like this. So the original ray travels this way. And here, when it enters from air into glass, it bends towards the normal. So make it bend somewhat like this. Again, when it enters from glass into air, it has to bend away from the normal. So this is the final ray that emerges out of the glass slab. So we have considered two rays that emerge out of the glass slab on the left side. And when they enter into the observer's eye, they appear to be coming from a common point somewhere here. This distance is what we are trying to find out. This is the final image. And that distance is what we are looking for. We know the refractive indices. The surfaces are flat, so the radius is infinite. Radius of the first surface tends to infinity. Radius of the second surface also tends to infinity. Fine. Can one of you tell me the steps that you need to take to identify that or to calculate that image distance finally? There are two refractions happening. What to do? Okay. Last class we discussed what to do if one refraction happens at a flat surface, that apparent depth and all. Like this example you can take. The object was inside glass. Light bends once at this surface, and this is where you get the image. And how did we find the image position in this case? Like we used a spherical surface refraction formula and all, but finally we showed that this can be found using the apparent depth formula. Okay, x is equal to d, the actual depth, into mu2 by mu1. We can find it out that way for a single refraction. Now, when multiple refractions occur, there's a simple idea that we are going to use. We'll first find out what happens due to the first refraction, then we'll find out what happens due to the second refraction. So there are two flat surface refractions happening here. Consider the first one. Okay, I'll copy this diagram. For the first one, we don't need the thickness and all. Assume the glass slab is very thick. So after the first refraction, light is going to travel, the light ray is going to travel like this. So after the first refraction, if I extend this ray in the backward direction, the image appears to form somewhere here, way behind. Okay, for now you don't need I dash. So assume the light just refracts once and enters into the glass slab. The light that enters into the glass slab seems to be coming from here. We'll call this as I1. Okay, and then what happens? That light which appears to be coming from I1, okay, strikes the second surface and again undergoes a refraction. So for the second surface, this I1 is where the light appears to be coming from. Therefore, I1, which is the image formed by the first refraction, becomes an object for the second refraction. The original object has nothing to do with the second refraction. Because for the second refraction, the way the light is striking the interface, it appears as if it is coming from I1, not from O. So I1, which is the image of the first refraction, will become the object for the second refraction. Okay, and this idea is very important, not just in this problem. Generally, whenever there are multiple reflections or refractions or combinations happening, image formed by the first reflection or refraction will be treated as object for the second one, because that is where the light rays appear to be coming from. And image formed by the second reflection or refraction will be treated as an object for the third reflection or refraction if it happens, and so on. Okay, this is the logic behind all that. Now here there are two refractions happening. So what we will do is we'll find out the image position due to the first refraction. We'll treat that as an object for the second refraction and find out the final image position. Okay, let us work on this first. Object is in air. You all know air refractive index is 1. Assume glass refractive index is mu. Okay, exact value is not given to you. Take it as mu itself. The object is at a distance L from the first surface of the glass slab, as you can see in the diagram. So that's the actual distance. One of you tell me, like, use that apparent depth formula and tell me how much is this? How much is the distance of I1 from the first glass surface? Let's call it x1 or d1. You can call it d1. x1, let's call it. Original distance of the object is L. What is the image distance from that flat surface? Okay, I got one answer as mu into L. That is correct. Okay. See, apparent distance will be actual distance into mu2 by mu1. We are going to use that formula as it is. Therefore, the apparent distance x1 becomes actual distance L. Now, which medium to take mu2, which to take mu1? Mu1 is the medium in which incident rays are present. Incident rays are coming from the object. Object is in air. So mu1 is that of air. Mu2 is the medium in which refracted rays are present. They are present in glass. So mu2 will be refractive index of the glass. So that will be mu into L. Okay. Now what is this mu into L? Mu into L is the image distance from the first surface. Why are we bothered about it? Because for the second refraction, which you can visualize in this diagram itself, for the second refraction, the rays appear to be coming from I1, not from O. So as I said, I1 is the object for the second refraction. So basically what we are indirectly finding out is the object distance for second refraction. And if you know object distance only, you can tell image distance. That's the idea. Okay, let's go back to the original diagram now, original picture, this one. Okay, let me copy this. The rays striking the second surface, which is the left side surface, appear to be coming from I1. Where is I1? I1 is somewhere back here. So I1 will be treated as object for the second surface. Can one of you tell me, like we found that this distance is mu into L. Okay. But how far is it? How far is I1 from the second surface? How far is I1 from surface S2? Rishi, just look at the diagram, tell me directly.
Mu L plus T, sir.
T plus mu L. Okay. That becomes the actual distance for the second refraction. Okay. So now the second refraction can be visualized like this. You need to get used to all this. For the second refraction, the original object doesn't even matter. Then how should we treat it as? Let's forget the original object. Let's remove the original object from all this. S1 doesn't matter. This refractive index doesn't matter. You can imagine it something like this now. Okay. And how far is I1 from the second refracting surface? This was T. So total distance is T plus mu L now. That will be treated as the actual distance now for the second refraction. And what do you have to find out? The apparent distance is what you have to find out. Apparent distance is from here to here, x. Okay. How do you find out apparent distance? Apparent distance is equal to actual distance into mu2 by mu1. This is where you need to be careful. Mu1 is the medium in which incident rays are present. For the second refraction, these are the incident rays. And where are they present? They are present in glass. So mu1 is that of glass and mu2 is that of air. Because for the after the second refraction, they are going into air. So for surface S2, these are the refracted rays. These are the incident rays for S2. Okay, so mu1 will be that of glass, mu2 will be that of air. So it becomes 1 by mu. Effectively, the answer you get will be T by mu plus L. That is the distance from where? That is the distance from the first surface. Okay, that's where the final image forms. Okay, let's go back to the original diagram now. So the final image that the person sees, that the observer sees, you can call it as I2, will be at a distance of T by mu plus L. Where was the object originally? It was at a distance of T plus L. From where? From the first surface. From the first surface, it was at an original distance of T plus L, but it appears to be at a distance of T by mu plus L. Mu being more than 1, T by mu plus L will be less than T plus L. So it appears closer. And what is the shift now? How much is the shift? This distance is what you call a shift, apparent shift. You can calculate it as original distance from the surface S2 minus the apparent distance from the surface S2, T by mu plus L. L gets cancelled. T into 1 minus 1 by mu is the shift. So how much closer it appears depends on the thickness of the glass slab and the refractive index of the glass slab. But anyway, see, you're not expected to remember this formula, but the ideas are very important. There are multiple refractions happening here. So what did we do? The image formed by the first refraction becomes the object for the second refraction. And then we find out where the final image forms. Okay, that is the idea. After that, what is left is just calculation. Okay, fine. Now let's consider one of the situations that we considered in last class, that we saw in the last class. Let's take this example. Here what is happening? The observer is holding a glass sphere. Glass is definitely denser than air in terms of optical density we are speaking. And you can see that the image of the mountain appears smaller to us. Okay. Whether it appears closer or not, we'll find out. Now, bigger, smaller magnification, we'll get to that. But for now, let us find out whether it appears closer or farther. Okay. So try this problem, all of you. Till now, we discussed about a glass slab which had two flat refracting surfaces. So we could use the apparent depth formula. If there are curved refracting surfaces, you'll have to use the curved surface refraction formula, spherical surface refraction formula. So suppose there is a glass sphere. Its radius is r, radius of curvature. Refractive index is mu. Assume there's an object somewhere here. When seen from the other side of the glass sphere, find out where it appears to be. Means you have to find out the image position or the image distance. But from where? From the left surface of the sphere. Okay. So for that, I'll have to tell you where exactly the object is or at what distance it is. Radius you know, and consider this original distance as L. Suppose the observer's eye is very close to the glass sphere. Very close to the glass sphere on which side? On the left side. Somewhat like this. So the original distance from the observer's eye to the object is 2 times the radius, okay, plus L. You have to find out the apparent distance. Does it appear closer, farther? And what is the apparent distance? Try. See, if it's difficult using these symbols and all, you can make use of these values. Let's say L is some 20 centimeters. And you can assume the radius to be, okay, radius appears smaller than L. So let's take it as 10 centimeters. Refractive index of glass, you can use 3/2. Okay, if expressing in terms of R and L is difficult, you can use these values and tell me a numerical value for the answer. Any answer, anyone? Okay, try. I'll give you 1 more minute. Okay, you can visualize the situation like this. Assume this is the glass sphere, side view of the glass sphere. We need to find out where the final image forms. Okay. Tell me, for the light to travel from the object all the way to the observer's eye, how many refractions does it have to undergo? 1, 2, or more than that? 2 refractions, obviously. Okay, Anugrah is asking, do we consider R positive for both refractions? See, it depends on the sign convention and the side on which the center of curvature lies. Okay, we'll discuss in the solution. I don't think it will be positive for both of them. For the first one, it will be positive. Second one, it will be negative. Okay, so there are 2 refractions. Listen, all of you, you have to imagine light going from the object to the observer, not just in this problem, in any problem that you solve based on optics. And one ray which is easiest to trace is the ray which undergoes normal incidence. Okay, so you can imagine a ray traveling this way. This is the first surface that it strikes. This ray undergoes normal incidence, so it won't bend. It travels straight. And then this is the second surface where it undergoes refraction. Again, this ray doesn't bend, reaches the observer's eye. You need to trace one more ray to locate the final image. Okay. So there are 2 refractions that are going to happen. No? Let's roughly figure out what happens at the first refraction. For that, I'll take help of another diagram. We know this is a glass atmosphere, refractive index is more than air and all. Let's ignore these distances also. Just we need a rough picture of what happens at the first refraction. So let's consider this another ray somewhat like this. The ray is about to enter from air into glass. Isha, quickly tell me what happens to light entering from a rarer medium into a denser medium. What happens to light entering from a rarer medium into a denser medium?
It bends towards the normal.
It bends towards the normal. Okay. Visualize the normal there. Normal is the line connecting the center to that point of incidence. It has to bend towards the normal. Now, how much it bends towards the normal, we don't know. Original direction of propagation was this. If it bends only a little bit towards the normal, like this, then the image will be formed here. Okay, means light will strike the second surface as if it is coming from here. That is one possibility. If it bends sufficient enough, okay, upon refraction, if the light ray bends sufficiently enough, it may even become parallel to the principal axis. Then for the second surface, second refraction, light will appear to be coming from infinity. That means this object forms at infinity. Not object, this image forms at infinity. That possibility is there. There are other possibilities also. This case is quite complicated actually. I mean, the possibilities are quite complicated. If light bends a little more towards the principal axis, this also could happen. Light will strike the second surface as if it is converging, not diverging. Light from a real object actually diverges, but the light striking the second surface could strike while converging. That possibility is there. And another possibility, if the light ray bends more than enough, this also could happen. Bends like this, meets the first refracted ray somewhere here and goes on to strike the second surface. Then in that case, this is the image formed by the first refraction. And for the second surface, light will appear to be coming from that point I1. Okay, so we first need to find out where is the image formed by the first refraction, because that image acts as an object for the second refraction. Okay, so let's do that. Consider the distances given to you. Visualization we have done, but it didn't really help us. There are many possibilities actually. Okay, radius of curvature is given 10 centimeters. So that's the distance from here to here. This is the pole for the first refraction. And from pole to object, the distance is given as 20 centimeters. 20 only, no? Yeah. So we have to apply the spherical surface refraction formula at that first surface. Rishi, tell me the spherical surface refraction formula. Okay, derive it once and memorize. It is mu2 divided by v minus mu1 divided by u is equal to mu2 minus mu1 divided by r, the radius of curvature. What we are looking for is the image distance, or is where the image is formed by the first refraction. So v is what we are looking for. Okay. You know how the rays are traveling. They are going from air into glass. So for the surface S1, first refractive index is that of air. Second refractive index is that of glass. 3 by 2, I'm taking it as 1.5. Okay. And rays are traveling to the left side. So anything on the left of the pole will be considered positive. Anything on the right of the pole will be considered negative. Any distance on the right of the pole will be considered negative. Let's substitute all this in the formula now. Mu2 is 1.5, that is 3 by 2 divided by V, minus mu1 is the refractive index of air, which is 1, divided by the object distance. Anugraha, tell me how much should we take the object distance? Plus 20, minus 20 or something else?
Minus 20.
Minus 20. From the pole, it's at a distance 20 on the negative side. So minus 20 is equal to mu2 minus mu1 divided by r. Radius is also to be measured from the pole itself. From pole to the center. Center is on the positive side, so plus 10. Okay, minus minus becomes plus. 3 by 2 minus 1 is 1 by 2. 1 by 2 divided by 10 is 1 by 20. Okay, right hand side we are getting 1 by 20. 1 by 20, 1 by 20 cancel. Means it becomes 0. So 3 by 2v is equal to 0. Can any of you tell me what this means? How much is v? Infinite. With v in the denominator, it is becoming 0. That means v is infinite. What does this mean? It means after the first refraction, the rays become parallel to the principal axis. This is how they are bending. Now, this was one of the possibilities that we considered, right? For the distances and the refractive indices that we had taken, it turns out that this is what is happening. Okay, so the rays enter into the glass sphere parallel to the principal axis. And they strike the second surface of the glass sphere also parallel to the principal axis. So where is the first image forming? First image is forming at infinity on the right side. That will now behave as an object for the second refraction. So where is the object for the second refraction? At infinity. So object distance will be taken infinite. Okay, and now let's solve let's solve for the final image. Okay, now the first object and all don't really matter. Refractive indices will write again. The rays strike the second refracting surface as if they are coming from infinity. Let's first visualize where the image is expected to form. On the left side or the right side or exactly at the center. What are the possibilities we'll see? Okay, these rays are coming from infinity. Okay, extend the one which is undergoing normal incidence because that will help us draw the ray diagram easily. Now consider this ray. It's about to enter from glass into air. Should it bend towards the normal or away from the normal? Any one of you tell me quickly. From glass into air, how should it bend?
Away from the normal.
Away from the normal. It was originally traveling straight, like parallel to the horizontal. Now, if it bends away from the normal, it is going to bend like this. So the image is expected to form somewhere on the left side. Okay, let's see if the spherical surface refraction formula gives us the same answer. The radius of curvature here is also 10 centimeters. Whether to substitute plus 10 or minus 10, we will see. For the second refraction, this point is the pole. Where is the object? Object is at infinity. I1 was forming at infinity. That becomes object distance. Image distance is what we need. And for the second refraction, rays are entering from glass. So glass refractive index becomes mu1 into air. Air refractive index becomes mu2. Apply the formula mu2 by v minus mu1 by u is equal to mu2 minus mu1 divided by r. R is the distance from pole to the center. Rays are going to the left. So for the second refraction, this direction is positive. This side is positive. This side is negative. For each reflection or refraction, you have to assign positive, negative separately, freshly. So for the second refraction, it will become minus 10. Okay. Numerator 1 minus 3 by 2 is minus 1 by 2 divided by minus 10. Minuses cancel. This becomes 1 by 20. And this is 0. 1 by V is 1 by 20. Therefore, V is equal to 20 centimeters. What does this mean? We got a positive answer. For the second refraction, positive means the left side. Therefore, the final image forms 20 centimeters to the left of the glass sphere. Okay, so let's draw the complete picture of what is happening to the light coming from the object. And okay, coincidentally, we took a symmetric case actually. Object was 20 centimeters on the right side on that side. We got the image as image at 20 centimeters on this side. Fine. So this ray passes straight without any deviation. One more ray if you take it like this. Actually, this is exaggeration. You should not have this much angle because paraxial approximation will not be valid then. But let it be. For our visualization, we are taking it like this. And inside the glass sphere, they travel parallel to the principal axis. And then once they are out, they appear to be meeting at 20 centimeters on this side. So this is what is happening to the light actually coming from the object. That's what the result shows. Okay, so this is the final image. First image formed at infinity, final image is forming here. Okay, any doubts in this? How we are applying the spherical surface refraction formula? Okay, I just want to ask you one thing, not ask you, I just want to explain something here. Now, when we consider the possibilities in this case, one of the possibilities that we considered was this. After bending at the first surface, the light ray strikes the second surface, or light strikes the second surface as if it is converging. Let's see what to do in that case. Consider a plane mirror itself. Now, in real life, any object you take, you look at any point around you, any particle around you, light falls on that particle and gets reflected, or maybe the particle emits its own light. In both cases, the light coming from the particle or the point object will be diverging light. Okay, what I mean is, if an object is placed here, you can see this object from any direction. That means light is spreading out from that object, from that point. Okay, so the light coming from that point is diverging. In such cases, we call this as a real object. Any object in real life, this is what happens. Okay, if that falls on the mirror, you know, image will form on the other side. It will be a virtual image, all those things. Plane mirror, no? What if by some means you make converging light fall on the mirror? What do we mean by converging light falling on the mirror? Let's say light rays like this. Take one this way. Just a moment. Let's say the light rays falling on the mirror are about to converge somewhere here. So they all strike the mirror as if they are trying to reach that point. Few of the rays I'm showing. Okay. Now these rays are incident rays. Incident rays are converging. They cannot be coming from a real object, because rays coming from a real object will always be diverging. These rays cannot be coming from a real object. Okay, let them come from wherever they are coming, doesn't matter. Maybe they underwent some refraction and bent like this. and they strike the mirror. Can one of you tell me what will happen to these rays after they strike the mirror? Will they meet anywhere?
So they converge in front of the mirror.
They will converge in front of the mirror. Why? Because they have to follow the laws of reflection. No, first one, the middle ray is incident along the normal. It undergoes normal incidence. It gets reflected straight back. Okay. The others, if you draw the normal at their point of incidence and you draw the reflected ray. Okay, assume this is the normal at the point of incidence. Draw the reflected ray. You will see that it will converge with the, it will converge towards the ray that is in middle. And it gets reflected like this. So they meet here. Same happens with the third one also. They meet at that point after reflection. And if rays meet somewhere after reflection, what do we call that point? We call that point as the image. So it's possible for a plane mirror to form a real image also in front of the mirror. Light is actually passing through that point. So this is a real image. Where is the object? We treat this point as the object. There's nothing actually present there. Rays are not even coming from there. Okay. But incident rays were meeting at that point. The point where incident rays meet or tend to meet is the object distance. The point where reflected or refracted rays meet or tend to meet is the image. Okay. But incident rays, wherever they meet or appear to meet, is the object position. So we have to treat that, that as the object. And there's nothing actually present there. We call this as a virtual object. Okay. And you apply mirror formula, you will find out, you can find out where the image is. Since this is a plane mirror, it's easy to visualize. Image will form at the same distance in front of the mirror where the object is behind the mirror. See, there's nothing actually behind the mirror, but the incident rays are traveling as if they are going to meet behind the mirror. So after reflection, they'll meet in front of the mirror. So the point where they appear to be meeting behind the mirror behaves as the object now, and we call it a virtual object. So let's go back to this case where one of the possibilities we considered was these rays traveling this way and tending to meet somewhere behind the second surface. In that case, you would have treated their point of convergence as the object, virtual object, and you would have solved the problem. Okay. We'll actually solve a problem. We'll understand whether to take the object distance, positive, negative, all those doubts will still be there. Okay. We'll discuss. Let's apply it to a plane mirror itself. Now you all know the mirror formula. 1 by V plus 1 by U is equal to 2 by R or 1 by F. Any of them you can use. Let's apply that to this plane mirror. How much is the radius of curvature of a plane mirror? Anyone quickly? Radius of curvature of a plane mirror.
Infinity.
Infinite. Focal length is also infinite. Okay. So R tends to infinity. So the right hand side becomes 0 or tends to become 0. If right hand side is tending to 0, it means 1 by U plus 1 by V plus 1 by U is 0. That means 1 by V is negative of 1 by U. That means image distance is the negative of object distance. This is always true for a plane mirror. Okay. Now, which side are the incident rays traveling to? They are traveling to the right side. So anything on the right side will be considered positive. Anything on the left side will be considered negative. So in this case, object distance is positive. You will get image distance negative. And that object is a virtual object. Okay. So whether it's a real object or a virtual object, it's not the location of the object that matters. It's the direction in which the incident rays are traveling that matters to determine positive or negative. And in this example, we see object distance being positive. It's possible for object distance to be positive if the object is a virtual object. For a real object, no. Rays will begin from that object and go and strike a reflecting surface or a refracting surface. So that side will be positive. This side will be negative. For a real object, object distance is always negative, whether it's a mirror, refracting surface, lens, glass slab, anything. For a real object, object distance will be negative. But for virtual objects, object distance will be positive because the incident rays are traveling as if they meet on the other side. That is where the object will be considered, and that's the side to which incident rays are traveling. So that side will be positive. So object distance becomes positive. Okay. Fine. Spherical surface refraction, sphere image you found, glass slab image you found. There's one derivation you need to do actually. I'll send you the derivation in the worksheet. It's nothing but lateral shift of a light ray. Okay, like suppose there is a glass slab and let's say you know its refractive index and its thickness. Okay. When light is incident at an angle like this, you know when it enters from air into glass, it bends towards the normal. So it bends like, okay, let's draw the original path of the light ray. This is the original path along which it was traveling. It bends towards the normal. And here it bends away from the normal. And finally travels like this. So you will have to derive this shift. Okay, that's called lateral shift of the light ray. You can extend this. This shift we have already derived. Okay, that is T into 1. What did we get? How much was the shift we derived? T into 1 minus 1 by mu. That shift we already derived. You'll have to apply some trigonometry and derive this. Okay, I'll send you the steps in the worksheet. You will be able to do it. It's there in NCERT also. This is important for board exam. Fine. Next is the case of multiple glass slabs or different media. But before that, solve this question. Suppose there is a spherical glass slab. Okay, I should not call it slab. Let's say there's a glass sphere. Radius of curvature is given to you. Take it as 10 centimeters itself. Refractive index is given to you 3/2. Assume there's a particle inside this glass slab. Okay, this is also a common question. Many of you might have solved it already, but do it once again. The particle is present here. Where exactly? 5 centimeters from the center of the glass sphere. That is its actual distance. So from this surface, it is at 5 centimeters actually. And from the opposite side, it is at 15 centimeters actually. But when you look at that particle from outside, okay, assume there's an observer on the left side and an observer on the right side. Light will have to travel this way. Light will have to travel this way to reach the observer on the right side. So it undergoes some refraction and then reaches the observer. So the observer won't actually feel it's at a depth of 5 centimeters from that surface. It may appear closer to the surface or farther. And if there's an observer on the left side, light will have to travel this way. Here it undergoes refraction. So the observer won't actually feel like it is at a distance of 15 centimeters. May appear closer, may appear farther. Find out how, or find out the apparent depth of that particle. I'll call the particle as A. Let the center be C. Find out the apparent depth of the point A when seen from this side and that side. I'll just draw the observer's eye. So one observer is looking at it from the left side, another from right side. Find out at what distance it appears to be. Solve this problem, all of you. It'll be better if you can first draw the rays roughly and like get a feel of whether it appears closer or farther. Okay, let's consider O1. Draw the rays and tell me, draw the rays roughly and tell me, one of you, when seen from the left side, will it appear to be closer than 15 centimeters or farther? It's very important to visualize how the rays travel. Okay. I think it will appear farther only. You imagine the rays traveling towards this observer. One ray travels straight without bending, normal incidence. Another ray, take it roughly incident like this. Now center is on this side. So the normal will be somewhat like this. And the light ray going from glass into air has to bend away from the normal. How can we tell for sure that it appears farther? We cannot. Bending away from the normal. If it bends too much, no. Too much means like this. Then this is where the image forms. The observer will feel it is very close to them. If it doesn't bend that much, it may even become like this, parallel. Then the observer will see it at infinity. If it bends only a little bit, then the observer will see it somewhere here, farther. So multiple possibilities are there for O1 actually. Unless you solve it, unless you substitute in the equation and solve, you can't tell. Okay, try this, all of you. Light is going to the left side, and for this refraction, this point is the pole. It's very important to visualize the pole because all distances will be written from there. Try. Radius is given 10 centimeters. Refractive index is 3/2. Okay. Rishi, can you unmute? We'll discuss.
Yes.
You need to find out where the image forms. Okay. That is where it appears to be. How much is the object distance?
Uh, 15.
Okay. Which way is the light traveling?
Towards the left.
Towards the left. So anything to the left of the pole will be considered positive. Any distance to the right of the pole will be considered negative. So we have to assign the signs first. Object is A. Okay, light is coming from A. It's on the negative side. So object distance should be taken -15. We'll do that. And from which medium to which medium is light traveling?
Denser to rare.
Okay, that's okay. That visualization of rays we have done already. Exactly from which medium to which medium? From glass to air. Okay. So first medium in which it is traveling is glass. So mu1 will be 3/2. Mu2 will be that of air, which is 1. And object distance is -15. You have to find out image distance. Radius also you have to see. Center is on the negative side of the pole. So radius will be considered negative. Therefore, mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. So that right hand side becomes -1/2 by -10 becomes 1/20. Let it be. 3 and 15 cancels 5 times, 2/5. Okay, 2 into 5 is 10 plus. So 1 by V plus 1 by 10 is equal to 1/20. So 1 by V becomes 1/20 minus 1 by 10. This is -1/20. Therefore, you get or you find that the image distance is -20 centimeters. Okay. Which means image forms on the negative side. Negative side means right side at 20 centimeters. Radius is 10. 10 plus 10, 20 means image appears to be here. So basically what happens, the rays that are actually emerging from this point bend before entering into the person's eye. They bend such that they appear to be coming from that point behind. Okay, so maybe they bend only a little bit such that they appear to be coming from slightly farther. Okay. In a similar manner, you can find out where that particle or the dot appears to be when seen by the other observer. But let's do a rough ray tracing first, just to find out whether it appears closer or farther. One ray travels straight towards the observer like this. Another ray, roughly if you take it this way, normal is like this. And going from glass to air, it should bend away from the normal. Bending away from the normal makes it bend this way. So the rays that are coming out on the other side appear to be coming from somewhere here. So to the other observer, it appears closer. Okay, you solve it later on your own and you send me the answer. Fine. Next class also, which will be on Thursday. Okay, wait, today is Thursday. Next class will be on Saturday. We'll do some more practice based on this, and we'll also discuss those cases of multiple glass labs. Okay, especially for JEE advanced, such questions are very important. I don't know why, but IIT people have a lot of interest in those cases. Okay, multiple refractions at flat surfaces. Okay. We'll work on that. Of course, curved surfaces are also important. Today you learned what to do if multiple refractions happen. So whether it's reflections or refractions, the image formed by the first reflection or refraction behaves as an object for the second one. The image formed by the second one behaves as an object for the third one, and so on. That is the idea, and you understand why it is like that. It all depends on the way light strikes a surface. Okay, so, and you also learned what is a virtual object. Okay, if incident rays are converging, their point of convergence will be treated as the object position. Okay, and reflection and refraction will happen accordingly. Such cases in refraction will come across when we discuss lenses. Okay, in lenses, these virtual object cases are very common. Okay. Fine, we'll continue on Saturday. Thank you all.